Hello everyone, I am Cosmin and I would like to discuss how we can turn standard EEG signals into images to leverage state-of-the-art machine learning methods in image recognition so that we can solve the hard problem of predicting autism in infancy. Apologies for the voice, please. So our agenda for today is we'll start by looking at why ASD is still a big problem today, how we have approached this early diagnostic problem, the rationale behind our implementation choices. We're going to have a look at some results and the future of this work. Autistic spectrum disorder, or ASD, refers to a range of conditions characterized by a reduced level of social interaction, impaired communication and language, as well as a narrow scope of repetitive interests and activities. Symptoms develop within the first 5 years of life and often persist into adolescence and adulthood. Intellectual functioning is extremely variable, ranging from profound impairment to, in certain cases, superior abilities. One in every 160 children in the world is diagnosed with ASD. As ASD is behaviorally and not biologically defined, the diagnosis in the first years of life when intervention should be most effective still remains challenging. However, in that case, developing useful biomarkers for detecting ASD symptoms might be helpful for implementing early interventions tailored to the individual needs. So this is why we're trying to do this early detection. The EEG or electroencephalogram data used in this work was collected in the first phase of the British Autism Study of Infant Siblings, or BASIS. This is a large-scale collaborative project aiming to understand the biological origin of ASD by following up cohorts of infants at high risk for this disorder. Infants participating in the study had an older sibling with ASD, and these are part of the high risk group. And the low risk or controls had siblings without ASD. Please note the requirements of siblings for all the participants here. Continuous EEG was sampled while these infants were sitting in their parents' laps. Um, at a distance of 60 centimeters from a monitor, watching 3 video stimuli, each lasting 30 to 40 seconds. You can see an image of an infant sitting in the parent's lap in the slide here, and in front was a monitor. Um, the 3 video stimuli that were used were the first one, a woman singing nursery rhymes or playing peekaboo, and this had a social aspect, so it was called a social video. The second one was with brightly colored toys moving and producing sounds. Just the toys moving on the screen is of a non-social aspect. So here we wanted to see the difference in behavior between social and non-social. And the third video, we had the same surrounding toys, the same brightly colored toys. This time were manipulated by a human hand. So the toys weren't moving on their own. Instead, we had a human hand moving the toys. So again, this is a non-social video because we don't have a face and we don't have people talking to us, but still we have a bit of a social aspect as the hand was moving the toys. So we care about the differences between these 3 videos. Okay, uh, 3 triplets of video stimuli were presented in random order. So we had the first video, the second, and the third, the second, the third, and the first, and the third the second and the first, 3 times 3, but random and constant across the triplets for each participant. So this resulted in 9 30 to 40 seconds of EEG segments. Infant's behavior during the EEG session was recorded with a video camera to remove periods of behavioral noise. This would be stuff like spontaneous crying, laughing, or simply not engaging with the experiments. So we had to remove this from the EEG data, and to do that, they recorded the infant. And you can see here a picture of the infant being recorded. 101 infants took part in the study, 53 high risk, again, with siblings that had autism, or older siblings that had autism, and 48 lower risk, with siblings that didn't exhibit autism or any other type of neurodegenerative disease. And these had ages between 12 to 15 months when they were recorded. Data from 13 infants was excluded because of technical failures. This was 6 high risk, 7 low risk. 2 infants fell asleep during the EEG session, 1 high risk, 1 low risk. So as you can imagine, it's quite challenging to do data collection from infants. And 1 participant in the high risk group missed the diagnostic assessment at the 36 months visit. And from the rest of the subjects, sufficient artifact-free EEG data was obtained for 39 low risk and 39 high risk infants. So this is our starting data set. Please note here that the data was collected between 12 to 15 months, and the label or the diagnostic was given at 36 months using an ADI or ADOS test. You have to note here that you cannot give a correct diagnostic of autism or ASD before 36 months because you cannot, it is not yet visible. So this is why this work is very important. So this shows how long it takes and how difficult it is to collect and get good quality data for this problem. And we will see later as well that there are other challenges. So data collected at 12 to 15 months, diagnostic at 36. So we have to train the networks on the data from 12 months and append the label that we get at 36. Okay, EEG was recorded using 128 electrode sensor net. You can see it here in the image, how the net looks like on an infant. And it was sampled at 500 hertz. This means that we are collecting 500 samples per second, 500 data points per second. 12 electrodes, which are most often contaminated, were removed from the analysis, and this gives us a 116 electrode layout. Data processing for these 116 electrodes was initially performed using field trip, and this was done by the BASIS people. And afterwards, we used internally, the Department of Computer Science at Berkeley, various Python libraries to further do data processing. The behavioral coding results were synchronized with the EEG, and the periods when the baby was not looking at the screen, performed gross body or head or arm movements, cried, or other interference, these were excluded from the analysis. Also, the raw EEG was inspected visually for artifacts. This is very important because EEG data is very noisy, and you need a lot of experts to vet it before you can do real analysis on it. Okay, each uninterrupted data period was segmented into 1 second or 500 samples each. You remember the 500 hertz, that means 1 second. So we have 500 samples of EEG segments, each with 50% overlap, starting from the beginning of a clean signal. So for every 1 second, we will have an overlap from the previous 1 second, half of it, the first half. Okay. In the context of ASD, cortical activity related to memory operations is present primarily in three frequency bands. The theta frequency bands, which ranges between 4 and 7 hertz, alpha 8 to 13 hertz, and beta 13 to 30 hertz. Uh, Again, remember that we have sampled EEG at 500 hertz. This means that we have a range between 0 and 250 hertz of signal. We don't really care about anything above 30 hertz because that doesn't have to do with anything memory related. Okay. These channels were used in this work, and a noise removal process was used since EEG signals from inference are particularly noisy, as we mentioned before. However, removing noisy EEG windows may result in losing part of their time dependency between samples. Our approach considers windows of an EEG signal independent of each other and only uses the order of the samples to represent the temporal aspect of the EEG signal. This was considered reasonable since the behavioral noise happens at different times in the experiment for each infant. Okay, so it is this was worthwhile mentioning because uh, primarily EEG is temporal based and a lot of work is done in the temporal sector. Here we have removed part of the temporal aspect primarily because we didn't have enough data from from the infants, and also the method that we use uses fast Fourier transform, and this takes out the temporal aspect. So fast Fourier transform was computed for each 1 second segment after removal of the mean or baseline correlation and applying a Hanning window. We can have an overview of the EEG data set in this table here. So you can see that the data is split according to the diagnostic of the participants received at 3 years of age, and these are actually our labels. So we have the first column, LR meaning low risk. These are the controls. Uh, and the rows, we have the different videos. The social, which is the Peekaboo nursery rhymes video. The hand, which are the toys manipulated with the hand, and the toys on their own. Um, Hashtag S are the number of participants. So for controls, we have 39, as we have noted in the beginning. And these are the number of not noisy 1 second fast Fourier transform windows. So for the social, 2,755, for the hand video, 3,061, and for the toy, 1,865, only for low risk, for low risk. High risk typically developing HRTD. This means that these were initially in the high risk group, but they ended up developing typically. So they have a sibling, older sibling with ASD. Here we have 16 participants, 16 subjects, and you can see the number of windows, 1,248, and so on. ATY is still high risk, but they developed atypically, not with ASD. So this would be dyslexia or other type of mild, mild disorders, but not ASD. Here we have 11 participants and their number of windows. And lastly, the ASD, we only have 12 participants and their number of windows. All these windows that you see here, this comprises, this is our data set. These were further transformed into RGB images, as we will see next. So traditionally, the raw values of electrodes or their spectral measures are used to represent EEG feature vectors in EEG data analysis. However, our approach does not take into account the spatial properties of the data. This approach, so classical EEG, does not take into account the special properties of the data. Each electrode being located above a region of the brain or having neighboring regions, and this is a problem. We further transform the EEG signals into an image that preserves the spatial structure of the data. To ensure that the relative distance between electrodes, the spatial aspect, is preserved within each EEG window, we use the azimuthal equidistant projection, or also known as the polar projection. So you might be familiar with this if you know the maps of the world that are plotted with one of the poles in the center and the other pole at the edges of the circle. So we obtained 2D electrode positions using polar projection obtained from 3D electrode locations, as you can see in these figures here. So in these figures, A, B, and C, we have topology preserving and non-topology preserving projections of electrode locations. So in figure A, that is the 2D projection of electrode locations using non-topology preserving or simple orthographic projection. Figure B, we have the real locations of electrodes in the original 3D space. These are actually the locations on the scalp, as you have seen on the electrode net picture. And figure C, we have the 2D projection of electrode locations using topology preserving azimuthal equidistant projection. So you can see here the main difference between A and C, and how this matters a lot when you're doing this type of analysis, especially when turning EEG signals into images. Furthermore, we use the multiple color channels to represent the spectral dimension of the data by encoding the alpha, beta, and theta frequency bands into the R, G, and B channels of an image. We have chosen these frequency bands because, as I've said before, cortical activity related to memory operations is present primarily in these frequency bands. Theta from 4 to 7 Hertz, alpha from 8 to 13 Hertz, and beta from 13 to 30 Hertz. The spatial distribution of behaviors over the cortex was represented by the image's width and height, and the distributed power measurements of the electrodes have been interpolated over a 224 by 224 mesh. This process was repeated for each of the three frequency bands of interest, theta, alpha, and beta, yielding three topographical activity maps for each. After that, the three spatial maps were combined to produce a three-channel view. So here, after all of this work, cleaning, using the Fourier transform, interpolating over this 2 to 4 by 2 to 4 mesh, we get an RGB image that has the three main frequencies of interest encoded in its RGB, and its size is 224 by 224 for each of the windows, for each of the FFT windows that we presented in the data. Now, to bring everything together, this is an overview of the data processing pipeline as we have discussed before. You can see how we can start from the raw EEG data on the left, convert it to 2D polar coordinates, extract our frequency bands of interest using a bandpass filter, of course, and convert them to RGB images by interpolation, which are then fed into a deep neural network for training, or as you will see, multiple deep neural networks for training. For simplicity and speed, we have merged all the non-ASD classes, high risk typically developing, atypically developing, so HRTD, ATY, and TD, into one class, and we named it simply non-ASD. You can see it here in this table. By creating this non-ASD class and trying to separate it from the ASD, the typical autism detection problem based on EEG signal windows is transformed into a binary image classification problem instead of a multi-class. And the new class distribution for the three stimuli is 81% non-ASD and 19% ASD, as you can see in this table. So we have 66 non-ASD participants or subjects and only 12 ASD. And you can see there the respective number of images, complete number of images for each of the stimuli. As you can see in this table, we have a very large class imbalance, which we will have to alleviate with bespoke sampling and early stopping techniques. Since we are working with images, instead of raw EEG data, we have opted for a convolutional neural network as the main model, as these are in the state of the art for learning image-like data. Convolutional neural networks, or CNNs, can detect and extract local informative patterns and excel when have a grid or volume-like input. Was there a question or something? No. Grid-like input, right? However, they suffer, as do other deep neural network models, from the vanishing gradient problem caused by the gradient of the error with respect to the weights when traveling through many layers of representation. This in turn makes the gradient become too small for learning, thus making it sort of vanish. This is why they call it the vanishing gradient. And it's not really sort of, it actually vanishes because the gradient becomes zero. This is a problem related to the depth of the network and is specific to deep learning models. So it doesn't necessarily have to be a CNN or a multi-layer perceptron. As long as we have too much depth, we need to alleviate it somehow. And the skip connections that are found in residual neural networks alleviate this vanishing gradient situation. This architecture is similar to traditional multi-layer convolutional neural networks, but it includes the so-called shortcut or skip connection. You can see it here. We have an image of it in the slide. The skip connection is based on the assumption that by attempting to estimate residual functions that were not adequately captured by blocks of convolutional layers, one can approximate the desired mapping. We can imagine an extreme case where if identity mapping is the ideal mapping, meaning the block doesn't do anything, the learning block, or this residual block, this model would better capture reality by setting f of x to 0, where in this image we have f of x plus x. If f of x is 0, in the case that we want identity mapping, the simplest would just be for the network to set f of x to 0, and this is easy to do when we have these types of skip connection. Directly learning such a mapping without the use of the identity mapping would be more complicated than just setting it to 0. So the shortcut or skip connection approach is used to train the model based on this identity mapping, which facilitates the propagation of the signals both forward and backwards. When ResNets were first introduced, 3 distinct models were released to demonstrate that the effect of the vanishing gradients can be alleviated at various levels of depth, and that increasing the model depth is not always necessary. In this instance, our preliminary experiments with the 50, 100, and 150 layer ResNet showed that all 3 architectures, when benchmarked, perform similarly. Thus, we opted for the ResNet 50, the smallest one, because it has fewer parameters, trains faster, and performs the same as the other 2 larger versions or older brothers. In order to speed up training, transfer learning was adopted. The types of convolutional kernels that the convolutional network learns when trained on images, especially in the layers closest to the input, are very similar to edge detectors, which have been traditionally handcrafted by computer vision experts and used in machine vision systems. The benefits of transfer learning were also confirmed in preliminary experiments, whereby leveraging existing pre-trained models on well-established datasets, training time was dramatically reduced. The class imbalance issue was addressed by using weighted random samplers, which gives specific weights to every EEG image belonging to a class, thereby producing a balanced mini batch when sampling. Moreover, the weighted random samplers with replacement was used, which means sampling the same data points multiple times to create a balanced mini batch, and thus creating a balanced training set of EEG images overall. Early stopping was used to combat overfitting, whereby we use a small part of the training data to stop the training process when it looks like this might become over specialized on the training data and damage generalization. And lastly, to make sure that the learning pipeline is robust enough to predict ASD from EEG, leave one out cross validation was used, where we take the data from one subject and use for testing, train on all the remaining participants' data, and evaluate on the test subject left out. We report two types of experiments. One, where we split the participant samples into 80% for training and 20% for testing. As you can see in this image here, this is also called an 80-20 split. Uh, where we use data from all of the participants. If we have a red, uh, yellow, and green participant, we take 20% of the images from all the participants equally. We hold out for testing and then train on the rest. A small balance validation set is built for each of the videos, for each of the stimuli. Um, and we build this by removing 12 ASD images and 12 non-ASD images. So 12 images at random from from both classes. Um, the training starts on the remaining EEG images without the validation and test set, and then we stop the training when the validation set tells us, and we evaluate on the test set. The second type of experiment, as I've said before, is the leave one participant out. Here, all 1 second EEG windows which belong to that participant, or all the images that belong to that participant, have been left out of the training set. Again, we and used solely for testing. Again, we build a validation set, but as you can see, we only use data from the remaining participants, and we extract 12 images from ASD and 12 images from non-ASD. Also, for all of the experiments, we use the standard Adam optimizer with a mini batch of 100 and trained for a set number of 100 epochs. And also a separate ResNet 50 was trained for each video stimulus, be it the social, the hand, or the toy one. All experiments were run with and without early stopping to alleviate overfitting, which was most evident in the leave one out experiment, as we will see later. Early stopping requires a validation set, and that's why we use the validation set. And it requires it to include images that are not used for training, as this is standard. Otherwise, if we use the images from the validation set in training, we would compromise. So a small balanced validation set is built for each of the stimuli, trained is built by removing 12 ASD images and 12 non-ASD images from the training set of that particular stimuli. Training starts on the remaining EEG images using the validation set prediction as this criterion for early stopping. And here you can see an image where we have the training and validation loss. And when the validation loss starts diverging from the training, that is when we should stop training, because that means that the model starts overfitting on the training data. Okay. And this is what we did, and this is why we got these good results, because we used the validation. Okay, these are some learning curves from and results from our 80-20 split. On the top, we can see learning curves for the three stimuli and also how early stopping impacts prediction accuracy. If we were to rely simply on the training accuracy and stop training when we have the best accuracy, we would have stopped training at 100% accuracy, and the performance on the test data would have been worse. The landmarks that you can see in the image here symbolize the epoch where the validation set had the best accuracy, and they are placed on top of the test set to illustrate how the validation and test set do not always agree. Sometimes the model will perform better on the validation set than the test. This is also evident in the table, where we can see that sometimes using early stopping damages our accuracy, as is the case for testing accuracy on the hand dataset. Yeah, you can see like that we have actually dropped in accuracy when we used early stopping. Overall, the benefits of early stopping are not really evident when we use an 80-20 split, as the results are quite good already. And we cannot really assess, we cannot really use this 80-20 split to assess accuracy um, of this problem, because we need to assess completely new participants and completely new people. So it makes a lot more sense to use accuracy in the leave one out scenario. So here we can actually see how overfitting becomes quite significant in leave one out. You can see at all the um, testing curves. Um, Especially when the participants of the minority class would be classified as ASD. So this figure shows training and testing accuracies per epoch for 4 random ASD participants. You can see their IDs on the right, and it shows that the network learns the training set quite quickly. So the learning curves for the training are on the top. Those are the ones that learn very, very rapidly. Um, rapidly, but the predictions on the test image of that participant that was left out fluctuate a lot. And you can see the fluctuations in the test set in the middle, where where all of the learning curves vary a lot. So the use of the simple early stopping technique adopted helps, and we can see where the adopted early stopping technique terminates the training process. This is indicated by the 4 early stopping markers in the image, and this is within the 100 epochs that we decided. So you can see here, early stopping is happening quite early. You can see epoch 10, epoch 12, so very early. And this shows that the model overfits quite rapidly in the case of leave one out. So it learns the participants, it learns the training data very fast, faster than when we're doing the 80-20 split. Lastly, we can have a look at average precision, recall, F1 scores, accuracies across all participants with and without early stopping to reveal this beneficial role of early stopping in the more realistic leave one participant out scenario. The results in this table reveal how the network massively misclassify ASD as non-ASD when training is done without early stopping. So just by looking at the bottom table, we can see that during training, actually our accuracy drops, but during testing, it is significantly improved. This is evidence uh, of overfitting, right? So the model learns the training data, memorizes the training data instead of generalizing. Yeah, so I hope it was quite evident why this is very important. Okay, so to recap, we have considered EEG as an image and formulated this ASD prediction problem as a binary classification problem. Our pipeline exploited polar projections to enhance EEG data proficiency when learned by CNN kernels, skip connections to alleviate vanishing gradients, pre-trained ResNets to leverage transfer learning and speed up training, and early stopping for overfitting. Promising results imply that there is latent structure in the EEG images, and therefore, presumably, the underlying brain processing. And this can serve as a digital biomarker of ASD in infancy, which is very useful. Future work is to treat this class imbalance and improve generalization by using more advanced schemes and the expansion of the sample of the ASD participant and formulate this ASD prediction as a multi-class. So instead of using binary classification, actually use all the four classes. And we have done this and have promising results, which are not yet published, but will be soon. Thank you for your time. I hope everyone enjoyed the presentation, and I am open to discussing any anything you might want on the matter.